it's come to my attention that there's other ways of solving second order differential equations by using the method of reducing to first order. And this method is this is the long way to do the second order problems. I forgot about this until now, so I was doing some review for my one class and I saw this problem come up, and then it asked you to reduce the first order and solve it, and I had no idea how to do it. So I spent time trying to figure it out, and I figured it out. But the problem was this. Now, let's say, like in my other videos, I'm not sure when I'm gonna put this in my playlist, but like in the other videos, if it's before this video or after this video, you notice that I always proposed the general solution, right? I'm gonna show you how to actually get to there. Well, because like in those videos, you solve the characteristic equation, you plug in you propose y equals e to the rt, do the whole thing like this, solve for r, right? R is equal to 0, r is equal to -1, and they just kind of memorize how to propose this solution, right? And if you didn't get to that video yet, you'll see that coming up. But I wanted to look at it if we're going to reduce to first order. So let's look at how to reduce it. So to reduce it, you're going to take y double prime, set it equal to some other variable. I like to use v to v prime. In this case, y prime would then be v. So you see we're just doing a simple substitution to reduce it to first order. So that's v prime plus v is equal to 0. I just plug that in. Now we can do this and we can solve for v. So this could be rewritten as dv dx is equal to -v. Separate the variables. This would be the natural log of v is equal to -x plus c. Exponentiate both sides. That would be e to the -x times a new c. I'll make it c1. Then we have v. Now we can plug back in for v. So we know y prime is equal to v, so y prime is equal to c1 e to the -x, right? And then we just do the same thing again, and we're going to integrate again. So now we just integrate both sides. Well, yeah, we just integrate both sides. You can pull out that constant, because this is here. This is dy over dx. Once again, you can separate, but it doesn't really change anything. You just integrate both sides. You're left with y is equal to, pull that c1 out, c1 e to the negative c1 e to the -x. Well, no. So, and then it's always going to be positive, and I'll tell you why in a second. And this would be plus c2. See, it almost matches it, but you see, the thing is about constants is whenever you have a number times a constant, it's always going to be some new constant, right? Whenever you take the square root of a constant, it's not necessarily going to change. It's just going to be equal to the square root of 2. If you have x times a constant, that's equal to x times the same constant. Doesn't change. But whenever you take a number and multiply it or divide, it becomes a new constant. The number is going to change, right? It's going to scale. So that's going to become a new constant. So that's why when we write this, we can technically, we didn't use C3, but It's equivalent to this over here, though, right? It's this still equivalent. It doesn't matter what's in front of it. A constant is a constant. As long as this one's different than that one, that's all that matters. It's the same thing. So that just shows you how to do it this way. Now, there's also the case that my professor actually didn't do this with us, but where you have nonlinear. So I'm going to make another video, a little video on an example where we have a nonlinear second order differential equation, where we're going to have to use Bernoulli's that we did in first order. I'm just applying the second order. It's pretty much the same thing, just a little extra step. So we'll look at that in the next video. I'm not sure, right? Once again, I'm not sure where I'm going to put this in the playlist. I'm either going to put it before mechanical vibrations or in the beginning of the playlist. But no matter what, this is good to, still good to see, right? So I'll see you in the next video.